Hello and welcome to the 6th episode of the SpaceFromHome podcast. My name is Daniel Verscharen and I'm a lecturer in space plasma physics at the University College London's Mullard Space Science Laboratory. In this podcast, I tell you a little bit about the work of space scientists and engineers during the time of the COVID-19 situation. The last week saw the presentation of the first images recorded by the Solar Orbiter spacecraft. You may remember from the first episode of the SpaceFromHome podcast that Solar Orbiter successfully launched in February of this year. It usually takes some time to get the instruments ready for their operation. This was also the case for Solar Orbiter, but now we can have a first look at the data from this ESA-led mission with a strong NASA participation. The in-situ instruments on Solar Orbiter, like the solar wind analyzer or the magnetometer, have been operational since mid-June. Although the official observing time for the remote sensing telescopes on board Solar Orbiter will not begin until November 2021, the science and instrument teams were able to take some test images with their telescopes in the past few months. These images are not even meant for a detailed science analysis, but they already reveal that Solar Orbiter's telescopes can keep their promise and pave the way for very exciting new science in the years to come. Solar Orbiter has 6 so-called remote sensing instruments. They are located behind little windows in the spacecraft's heat shield to be protected from the harsh radiation environment in space and near the Sun. You can see the positions of the little windows in this photograph of the spacecraft that was taken before launch. They are under these covers on the front, which can be opened when the instruments are starting their observations. One of these remote sensing instruments is the Extreme Ultraviolet Imager, or EUI for short. Our institute took a leading role in the design and building of this instrument. As the name suggests, it observes the Sun in the ultraviolet part of the optical spectrum. This is light with even shorter wavelengths than the blue light that we can see with our eyes. The Earth's atmosphere blocks most of the ultraviolet light from the Sun, which is very important for life actually. However, this also means that we cannot observe extreme ultraviolet light from the ground. This image from Solar Orbiter's EUI telescope shows the Sun's full disk in the ultraviolet light. As you can see, it looks much more interesting than in the normal optical light that we can see with our eyes. Instead of seeing the Sun's surface, we now see the solar corona, the upper parts of the Sun's atmosphere. The corona is a few million degrees hot, much hotter than the Sun's surface, which has a temperature of just 6,000 degrees. We see brighter and darker regions, and also some large-scale structure, like the dark regions over the Sun's poles in this image. This picture was recorded on the 30th of May, when Solar Orbiter was about halfway between the Sun and the Earth. No telescope had ever been that close to the Sun before. This image shows high-resolution images also from EUI. The solar corona shows a remarkable fine structure. We see arcs of hot coronal plasma, which are held in place by the Sun's strong magnetic field. We see small regions that flare up in bright UV light. In these regions, the Sun's magnetic field changes its configuration and releases energy. These so-called nanoflares have never been seen with such a great resolution before. Because of the distributed appearance of these flares, the EUI scientists have said that the nanoflares look like campfires on Earth observed from an airplane. These campfires in the corona may play an important role for the heating of the corona, an outstanding unresolved problem in solar physics. As I said before, these images are still only test images for the telescopes before the actual science phase begins. Nevertheless, we already see that the images have an amazing degree of detail, and we even discover new things here. Another telescope on board Solar Orbiter is the Phi instrument. Like most instruments, it actually consists of multiple telescopes that can observe different things in the Sun's atmosphere. This Phi image, for example, shows the magnetic field on the surface of the Sun. The red and green spots show the polarity of the local magnetic field. As you can see at the Sun disk center, there are varying polarities next to each other. However, when you look at the bottom right corner of the image, you see a large region with opposite polarities. This is an active region where energetic particles can be accelerated or eruptions can be triggered. Phi can do even more. It can also measure motions and oscillations of the Sun, like little sunquakes. And much like with earthquakes, we can learn more about the interior of the Sun from the analysis of these oscillations and of the waves that propagate through its interior. Another remote sensing instrument is Metis. Metis is a coronagraph. It means that this instrument has a cover in the center of its field of view that occults the bright surface of the Sun. Outside of this central occulted part of the field of view, we then see the solar corona, the hot outer atmosphere of the Sun. This image from Metis was recorded in the visible light. We see that there are streams of plasma near the Sun's equator, which form the solar wind. Over the poles, the corona is somewhat fainter, although it also has some interesting structure there. These images will look very differently when the Sun is more active during its natural activity cycle in the coming years. Here you see an image taken by the SPICE telescope. SPICE is a UV spectrometer. This means it can observe structures in the corona in the range of ultraviolet wavelengths. Unlike the EUI telescope, however, it can measure very narrow ranges in wavelength. This allows us to study the elemental composition of the Sun's atmosphere in great detail and also its temperature. Here, for example, you see structures of carbon in the Sun's atmosphere with a temperature of about 50,000 degrees. Also, this material is held in place by the Sun's magnetic field. SPICE can measure many different elements and their properties in the solar atmosphere. One thing that is really exciting about SPICE is that we can use the observed composition at the Sun, for example, how much carbon, oxygen, or iron is present, and compare that with the composition measurements taken at the spacecraft. Our SWA instrument, led by our institute, will also measure how much carbon, oxygen, iron, and so on is present in the plasma at the location of the spacecraft. If you combine this information, we can get a very clear picture about where the solar wind is coming from. With SPICE, we can see it from the distance, and with SWA, we can sniff the composition right at the spacecraft. This combination of knowledge will enable very exciting new research directions that hadn't been possible before Solar Orbiter. The heliospheric imager, called SoloHI, is another telescope. It looks to the side of the Sun so that we can actually map the propagation of mass ejections or blobs in the solar wind. Here you see one of the first images from SoloHI. The Sun is on the right. However, the bright light that you see here is not the Sun itself. It is light reflected off the spacecraft's solar panels and then onto a baffle which protects the instrument. The little dot that you see on the center left is Mercury, and the bright bulge on the right-hand side of this image is caused by the reflection of sunlight on dust particles in the solar system. This is the so-called zodiacal light. The sixth member in the remote sensing family is STIX, an X-ray spectrometer. This telescope measures even more energetic photons than the ultraviolet telescopes on board. They are usually excited during solar flares, those bright eruptions of active regions. At the moment, the Sun is pretty quiet and we don't see many flares. Nevertheless, STIX measured an X-ray signal from a rather weak flare in June of this year. In this image, you see the location of the flare and the measured X-ray spectra. When such a flare happens, the coronal material gets heated to over 10 million degrees. These are very energetic events. The STIX instrument will see a lot of these events when the Sun gets more active in the next couple of years. As you have seen, there's already a lot of interesting material in the first images taken with Solar Orbiter. As time goes on, the spacecraft's orbit will bring the satellite closer and closer to the Sun. This means, of course, that the images will get even better. At the moment, the closest approach to the Sun was about 77 million kilometers. Later in the mission, we'll go to a distance of just 42 million kilometers. Of course, we then expect an even better view at the very important small-scale features in the Sun's atmosphere and on the Sun's surface. At the same time, the spacecraft will leave the plane of the ecliptic, which is the plane in which the Earth orbits around the Sun. That has never been done before by a spacecraft with solar telescopes on board. It will allow us to get the first images of the poles of the Sun. The poles play a critical role for our understanding of the processes that generate the Sun's magnetic fields, which are so important for all the processes we observe in the Sun and in the solar wind. Solar Orbiter is really unique. Combining data from 6 remote sensing telescopes with data from 4 in situ instruments on one spacecraft has never been possible before. This is truly a new era in the fields of solar physics and space physics. We are now in a position to explore our central star to an unprecedented degree of detail and through an unprecedented combination of measurements and observation techniques. Remember that we are just at the very beginning of a 10-year or even longer mission, and that these images only show test images before the official begin of the remote sensing science phase. I'm very happy to see that all instruments work so well and that we can already receive promising and exciting data from the mission. It will be even more exciting when Solar Orbiter is fully operational and when the orbit has brought us closer to the Sun or even out of the ecliptic plane. If you like this short look into Space from Home, please like and share this video, and then hopefully I'll see you around next time. Until then, take care and stay safe. Goodbye.